particle sorting. So last time we were looking at the number of particles we'd found in this particle zoo, and there are more that come later, but let's just have a look at those we've discovered so far and see if we can put them into any categories, including the ones that we've already got names for. So we can write down here the name of the particle. I'm going to make a table here, and you should do the same thing. So name of the particle. Let's have the charge of the particle. We could have the... what else could we have? We could have the rest energy. And I'll tell you what that is in a second. Energy of the particle. And we could have how it interacts. Just like that. And let's put down here some units. Actually, let's not bother with units. I'll do not bother with units, a physicist. We'll do charge in terms of the proton charge. So let's write that down. Proton charge, or the elementary charge, and the rest energy, we'll do that in units of mega electron volts. Now, you don't know what that is yet, but don't worry, the answers will be coming. And we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We're going to do 11 particles. So let's make my table have 11 rows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 8, 9, 10, 11. I think that's about there-ish. And we're going to fill in some details about some of these particles. So let's start with the ones that we had named. We've got the proton. We've got the neutron. We've got the electron. We've got the electron neutrino, so named already. And then we can look at their charges. So this was +1, this was 0, this was -1, this was 0. We look at the rest energies in mega electron volts. This was 930, let's say 8. This was 939, so only slightly more massive. Electron, much lower. The neutrino is very, very low. I mean, it's not actually 0, but it's very low. So I'm going to put 0 because it's really, really low. And now this is where it gets interesting, because in terms of the interactions, the proton interacts with the strong, the weak, and the electromagnetic. And I'm going to ignore gravitational because it's impossible, really, to determine the gravitational interaction for particles on this sort of scale. They're so low mass. How are we going to detect any gravitational interactions? Neutron is strong and weak, but it doesn't interact with the electromagnetic force. Whereas the electron is the weak and the electromagnetic. It doesn't interact with the strong nuclear force. And the neutrino is just the weak. It doesn't interact with the strong or the electromagnetic force. So you can see straight away there seems to be some differences. These two at the top, they seem to interact with the strong nuclear force. The electromagnetic force is the particles that are charged, so that's easy to explain. But they all interact with the weak nuclear force so far. So then we say, well, let's have a look at any other particles. And we can go through the list. And of course, these have got antiparticles as well. The antiproton, the antineutron, the anti-electron, the anti-neutrino. And I'm not going to bother writing all of those down, but all it means is that we reverse the signs on the charges. That's all we're doing in those antiparticles, reversing the signs on the charges. So let's add our new particles then. We've got our pions. Now, we didn't call them pions at first. It went like this. We had particles, 3 of them, that we discovered with these 3 different charges. And they had rest energies of about 140, but these were slightly lower, 135 mega electron volts. That was interesting. They interacted, all of them, with the strong nuclear force. They also all interacted with the weak nuclear force, although we couldn't detect that interaction at this time, so I'm going to leave that blank. These interacted with the electromagnetic force, whereas our neutral ones in the middle didn't. Now you can see clearly there is a way of categorizing these particles by their rest masses, their rest energies. We use the terms interchangeably. These are up at the top end. Then we've got these in the sort of the middle. And then you've got these right down at the bottom end, with the neutrinos being so small that you can't really write down what it is. It's too small. So, okay, we give them names and we say this is a pi plus, this is a pi 0, this is a pi minus. Fine, we've given them names. And then what do we discover? Well, we discover three particles that seem to have the same charges as the pions. They seem to interact in the same way, strong nuclear force, and the electromagnetic force for the charged ones, and the weak nuclear force, but we didn't detect that straight away, so I'll leave that out. But their masses seem to be a bit different. They were about 494, 494, and 498. So all around about the same amount, but different again. There was a step up. So if I show you now our categories, we've got high mass up here, then we've got slightly lower mass here, then we've got slightly lower mass again, and then we've got absolutely tiny masses there. But the weirdest thing was that these newly discovered particles with properties very similar to pions, but more mass, you'd expect them to decay more quickly because they've got more mass, but they lasted a bit too long. So we gave them a new name and we called them kaons. This isn't the whole story, of course. There's more to it. And I haven't included muons yet, so I should probably put muons on this list as well. And our muons, there they are. Where do they sit in all this? Well, they have a charge of -1, just like the electron. They interact not with the strong force, but with the weak and the electromagnetic force, just like the electron. But their mass is bigger than the electrons, about 200 times bigger. So now you have a look and you say, well, what's going on now? Because should I put these particles in the same category as those? They've got very similar masses. Remember, rest energy and mass, I'm using those terms interchangeably, but their interactions are very different because the pions, as we named them, interact with a strong interaction, whereas these muons, as we named them, don't. So they aren't the same category. And then you think, okay, so perhaps we should say that all of these particles that don't interact with the strong nuclear force belong in one category. We take them out, and then we go, well, what have we got left? Now we've got high mass, medium mass, well, somewhat medium mass, and then lower masses like that. Maybe there's three categories of the strong interacting particles and the other type of particle that doesn't interact with the strong nuclear force. Maybe. So this is the game. This is called taxonomy, sorting things into categories. And it's a scientific skill that's required, is the ability to sort and see patterns. But there were more particles discovered as well that I haven't included in this list. So the ability to spot these patterns became harder and harder and harder. I will just point out at this point that I haven't included the antiparticles for most of these, but you've got things like the antiparticle for the proton is the, oops, choose the right pen. The antiparticle for the proton is the, let's put antiparticles. So the antiparticle for the proton is the antiproton. For the neutron, it's the antineutron. For the electron, it's the positron. We don't tend to put a bar over the top for the positron, which is fine. I mean, sometimes people will put a plus there for the proton, but then when you do the bar over the top to make it an antiproton, does that little plus, does that mean that that has a negative charge? What's going on there? Then we have our neutrinos with our antiparticles for neutrinos with a bar over the top. We've got our muons don't put a bar over the top, we put a plus instead. I mean, there's some clues there about how we sort the particles by how we actually label them. But then there's these. What's going on there? And it was thought that maybe the pi minus and pi plus, one of them is the antiparticle and one is the particle. Maybe the k minus and k plus, one of them is the particle, one is the antiparticle. We didn't know. And if that's the case, what's going on with the neutral charged versions of these? That was the question. So we figured it out. Well, I didn't figure it out. This was before I was born. It was figured out. The first thing we're going to say is that particles that interact, I think that's how you spell interact, might only have one R. I think it's only got one R. Interact with the strong nuclear force. We have a special name for them now. Hadrons, or hadrons if you prefer, which I don't. Hadrons. That is just what we call these particles. That is it. And that makes protons, neutrons, pi plus, pi 0, pi minus, k plus, k 0, k minus, all hadrons. But it makes the electron, the muon, the neutrino, not hadrons. So what do we call those? Well, we call them leptons. So we can write this down. Leptons. Particles that don't, let's write it in full. Particles, I should say that, not the. Let's delete that and rewrite it. It's worth making your notes look good. That interact, or let's say do not interact. Do not interact with strong nuclear force. We call those leptons. That's just what we call them. Now, the etymology of the word lepton is interesting. The lept part, I believe, is the same root word as in leprechaun, as in very, very small. So that would make these things leptons, and these things leptons, and these things leptons, named after the fact that they are the smallest mass, the smallest rest energy of these particles. Yes, I do keep saying rest energy and mass. I'm using the terms interchangeably, and that is because of, might as well get this in the notes, that is because of E equals mc squared. So rest energy is the energy that is equivalent to the mass of the particles. And that's why I'm using those terms interchangeably. Well, that would make protons, neutrons, pions, and kaons all hadrons. There's a lot of particles in the hadrons category. And that is what they're called. So leptons, etymology of that word is small, light, Hadrons, they tend to be the ones that are more massive. Because they interact with a strong nuclear force, they get put in the hadron category, not because of their mass. There is a particle that is a lepton called a tauon, or a tau particle, which is much more massive than the muon, and therefore more massive than pions, but it still counts as a lepton. So the etymology, the idea of lept, meaning small, that doesn't really work anymore. Might be where the word comes from, but language evolves and changes. We don't speak English, we speak physics. So, yeah, we said the thing. Right, so let's have a look at hadrons in a little bit more detail. So hadrons, these things, all experience a strong nuclear force, yes. They also all, charged ones, interact with the electromagnetic force. What about the 𝗨0 and the K0? Do they interact with the electromagnetic force? Well, they don't have a charge, so not really. But we'll look at the internal structure of them later and see that actually internally they can do, and they do. They all have mass, and therefore we would expect them to interact with the gravitational force as well. And actually, although it isn't written here, they all interact with the weak nuclear force as well. That was discovered. And the weak nuclear force actually decays these particles. So pions, pi particles, decay by the weak nuclear force. You might want to actually write what these abbreviations are, otherwise you're going to get lost. Nuclear force. Neutrons also decay by the weak nuclear force, but protons don't decay. They are stable. So what's going on there? And what do neutrons decay into? And what do pions decay into? And this is going to help us unpick what the difference is between the types of hadrons. So it turns out neutrons decay by the weak nuclear force into protons. And there are other particles we discovered, like the delta particles, like the sigma particles, like the omega particle, like the xi particle, that decay into protons. So there seems to be one group of hadrons that decays into protons, and then there's another group of hadrons that doesn't. The pions and the kaons don't decay into protons. They don't decay into protons. So I'm going to put this down. Pions decay by the weak nuclear force, but not into protons. Then we've also got the kaons, and they decay by the weak nuclear force, but not into protons. So we seem to have some particles that are proton-like in the sense that they decay into protons. That's the neutrons decay into protons, and the protons themselves are already protons. These are sort of proton-like particles. The proton would be one of them, the neutron would be another. And then we've got some particles who behave differently because they don't decay into, what color shall I use for this? Let's use blue. They don't decay into protons. They are different. Is that going to erase the W from the... No, that's fine. I was worried that highlighting blue over a blue pen would make it invisible, but it doesn't. Oops, got a bit wonky with my lines. There we go. Those particles seem to be different. So we've actually got three categories of particles here. Yes, the pions and kaons are somehow different. The kaons are strange in their large masses and yet unusual stabilities. But we've got these three categories. Those highlighted in yellow are hadrons that decay into protons or already are protons. The ones highlighted in green are leptons that don't experience a strong nuclear force. And the ones highlighted in blue, well, they are something else, a type of hadron that doesn't decay into protons. And we have names for these things. Of course we have names for these things. So we can say that we call them baryons. Bary means big. Baryons decay, and they are hadrons. Let's put this, are hadrons that decay into protons, or already protons. They're part of the proton decay chain. Whereas mesons, and meso means medium, are hadrons that do not decay into protons, or perhaps I should say they're not part of the proton decay chain. So, highlighting in yellow, to keep all our notes consistent, highlighting in yellow, our protons and neutrons are baryons. Our mesons, on the other hand, we highlighted in blue. So let's get that out. Mesons, hadrons that don't decay into protons. And because they're hadrons, I can highlight the word hadrons in red, really trying to graphically get your head around the idea of these different categories of particles. In fact, we could even draw a sort of a tree, a diagram, showing the relationship between these, maybe even an Euler diagram. We have sort of matter-like particles, so that includes matter and antimatter-like particles. And within that, you've got hadrons, or hadrons if you prefer, which I don't, and leptons. They're two categories. And within the hadrons, you've got baryons, spell it right, baryons, and you've got mesons. So mesons are one type of hadron. Baryons are another type of hadron. Sometimes mesons pronounce mesons. I don't like that. They're all hadrons. We've also got leptons as a separate category, and they are all matter or antimatter. You get matter or antimatter versions of these. Well, mesons are interesting in that regard, and we will get onto that a little bit later. So hadrons, let's use my color highlighter. Let's try to be consistent with our notation so that when we come to revise, we've got that extra little bit to help us. Do I use green for leptons? Yeah, I use green for leptons. Of course, next lesson, I'll forget all about this and use different colors. So that is how we can categorize particles. And we can put particles into these different places. We could say, for example, protons, neutrons, pions, kaons, electrons, muons, positrons, antimuons, electron neutrinos, electron antineutrinos. We have actually also got muon neutrinos and muon antineutrinos, and we'll come to that later as well. With the kaons, we've got plus, minus, zero, and anti-zero. With the pions, we've got plus, minus, and zero. We've got antiprotons. We've got antineutrons. There's loads of particles, and we can put them into one of those three categories: baryons, mesons, leptons. Baryons big, mesons medium, leptons small. Big, medium, small. Doesn't quite work out that way, but that's what they were named for. So we want to make these new particles. I mentioned that last time. And we use particle accelerators to collide particles and convert the energy of that collision into mass, into particles, the rest energy of the particles. And that is conserved. We don't destroy energy in a sense, but sometimes the energy manifests as the rest energy of the particles. That's the energy the particles have as a consequence of having mass, the energy that's locked away in their mass. And I will say no more about that because I think that should be the end of this lesson. Yes, that should be the end of this lesson. We've talked about sorting particles, but of course, there is more. There is more to be done on this topic. Of course there is. Hopefully you found that useful.